Hello there and welcome back to the Science Sleepy Minds, where the temperature's imaginary, the equations are cranky, and you're about to spend 29 straight minutes pretending that a black hole is somehow cozy. Picture this. You're drifting quietly in deep space. No sound, no pressure, just you and the looming silhouette of a black hole. It's absolutely black, not turn the lights off black, but not even light can escape black. And yet, strangely, it has a temperature, a heat signature, a whisper of radiation tickling the void. You float closer, half curious, half insane, staring down the one thing in the cosmos that devours everything and still manages to sweat. You probably won't survive this. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop your location and local time in the comments. I love seeing where in space-time you're tuning in from. Now, dim the lights. Maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You begin your slow, steady drift toward a Schwarzschild black hole. It's the classic kind. No spin, no charge, just raw gravity sitting there like a cosmic pothole. From a distance, it's calm, silent. Your instruments show nothing. No photons bouncing back, no sound, no magnetic field. But there's a strange chill to it, like standing too close to a heat lamp you can't feel but know is there. And then the whisper begins. Not a sound exactly, but a hunch in your bones, like space itself is holding its breath. You're not falling yet, not technically. You're just coasting, letting the gentle tug of gravity stretch your limbs, your thoughts, your patience. There's no clear boundary, but around the so-called event horizon, the no-return line, the laws of physics begin to twitch. Here's the fun thing no one tells you about black holes. They're not actually holes. They're more like bruises in the fabric of reality. You can't go around them. You can't look inside them. You can only orbit them, theorize about them, or, if you're Stephen Hawking, insist they might slowly evaporate. And here comes the weird part: heat. A black hole has a temperature. You're forgiven if you assume these things are frozen solid death machines. Most people do. But they actually radiate energy, slowly, imperceptibly, like the world's worst space heater. This is where our journey really begins, in the contradiction. A black hole, by definition, emits no light, and yet it leaks. It has entropy. It decays. These are all thermodynamic terms, words we usually reserve for things like steam engines and sunburns. But here we are, pinning little thermal post-its on a black void 10 million times the mass of the sun. You float there now, instruments humming softly, measuring background radiation levels. They're minuscule, barely above absolute zero, but they're not nothing. This is Hawking radiation. It's the last breath of a black hole, a faint stream of particles that somehow emerge from the vacuum. More on that later. What you're watching, from your perfectly safe and highly implausible observation capsule, is the beginning of the end. Not yours, not yet, but the black hole's. It's losing mass, atom by atom, over eons. If it could scream, it would be a whisper trailing off into infinity. Let's rewind the physics clock a bit. Back in the 19th century, thermodynamics ruled the world. Engineers and physicists were obsessed with heat, pressure, energy, how to trap it, harness it, and measure its waste. In that golden age of steam, scientists laid out the great laws of thermodynamics, rules about how energy moves and how you can't really win, only break even or slowly lose. Fast forward to the 20th century. Einstein drops general relativity on the world like a gravity-flavoured pie. Suddenly, mass bends space, time isn't linear, and if you pack enough stuff into one point, space-time folds in on itself. Boom! Black hole. But here's where things get awkward. Thermodynamics tells you nothing, ever disappears, energy is always conserved, entropy always increases. So when you throw something into a black hole, a star, a book, your weirdest thoughts, you expect that information to stay somewhere. Spoiler, black holes don't give receipts. At least they didn't until 1972, when physicist Jacob Bekenstein proposed something truly unhinged, that black holes have entropy. That they aren't just vacuums, but thermodynamic objects with a kind of heat content. People laughed. Some still do. But Bekenstein pushed further. He said the entropy of a black hole should be proportional to the surface area of its event horizon. Not the volume. This was absurd. Entropy usually depends on volume. It's like saying the messiness of your house is based on how dirty the outside of your windows are. Still, this idea planted a seed, and in 1974, Hawking dropped the radiation bombshell. Using quantum field theory and curved spacetime, casual, right? He showed that black holes must emit particles, that vacuum fluctuations near the event horizon could lead to one particle escaping while its twin falls in, causing the whole to lose a tiny amount of mass, and thus black holes evaporate, very slowly. You'd need longer than the current age of the universe for a stellar mass black hole to fully disappear. But the process exists. It has a temperature, an entropy, and, this is the kicker, it obeys thermodynamic laws. Sort of. Historians still argue whether this discovery really saved the laws of physics or just added a decorative hat to their funeral. Because even if you can assign temperature and entropy to a black hole, you still can't retrieve what you threw in, not without quantum gymnastics and a PhD in holographic guessing. You float there, absorbing the contradiction. You feel the coldness of infinity and the heat of an idea, that maybe even the darkest thing in the universe has rules, that maybe heat and gravity are two faces of the same weird coin, and that terrifyingly that coin is flipping right in front of you. Behind you, your engines purr. In front of you, the event horizon looms. It's not glowing, it's not sucking, it's just waiting, like a cosmic thermostat that only kicks in after 1 trillion years of silence. You press in closer, letting the blackness fill your field of view, not because it's doing anything dramatic, but because you're still trying to wrap your head around one stubborn fact. This thing has a temperature. That's not supposed to happen. Temperature in your everyday life is the jostling of particles, atoms bouncing around, crashing into one another, transferring energy like over-caffeinated toddlers in a ball pit. And black holes don't have particles, at least not that you can see, not inside, not outside, nothing comes out. So where is the heat hiding? It's that pesky Hawking radiation again, that almost imaginary whisper of particles born from nothing, dancing just long enough to say, hey, physics is weird, before vanishing back into the void or escaping into the universe. And here's where things get confusing in a delightfully forehead-slapping way. Black holes have temperature, yes, but they also have inverted temperature logic. The more massive a black hole is, the cooler it gets. A black hole with the mass of the Sun has a temperature of about 60 nanokelvin. That's colder than cosmic microwave background radiation. You'd freeze to death before its warmth reached your marshmallow. But as the black hole evaporates and loses mass, the temperature creeps upward. It begins to glow, not visibly but mathematically, until it reaches a runaway point where it burns up into a final vanishing blaze. The universe's most lethargic fireworks show. Now let's do the awful math. You take the formula Hawking derived. T equals h bar c cubed divided by 8. PGMKB, where T is temperature, h bar is the reduced Planck constant, c is the speed of light, g is the gravitational constant, m is the black hole's mass, and kb is Boltzmann's constant. Yes, there will not be a quiz. What matters is the bottom line. Temperature is inversely proportional to mass. So as m goes down, T goes up. That's the opposite of how, say, a star works, and the fun doesn't stop there. A black hole's heat capacity, how much energy it needs to change its temperature, is negative. That means the more energy it loses, the hotter it gets, which makes it lose energy faster. It's a death spiral disguised as a space campfire. Let's back up to that lovely idea of thermodynamics again. Specifically the Zeroth law, which says that if two systems are in thermal equilibrium with a third system, then they're in equilibrium with each other. This leads to the idea of a uniform temperature. Does that hold here? Sort of. A stationary observer hovering near a black hole would measure an incredibly high temperature due to gravitational blue shift. The photons from Hawking radiation get jacked up as they climb out of the hole's gravity well. But someone far away, like you, gets a tamer version. The cooled down echo of that radiation. So, temperature is relative. Yes, just like your ex's opinions. And the first law? It kind of holds too. The black hole's change in mass can be thought of as equivalent to energy loss, a la E equals mc squared. But instead of internal energy and volume, you get mass and surface area. Because again, black hole entropy is tied to surface area, not volume. We'll beat that dead horse later. There's something deeply satisfying about this. You're used to heat being a byproduct of life, or friction, or decay. But in a black hole, heat becomes a consequence of curvature. Space-time bends so violently that even the vacuum spits out radiation. You remember that historical gem? In 1975, shortly after Hawking published his radiation theory, many physicists were skeptical. The idea that the coldest, deadest object in the universe could emit anything, let alone follow a thermodynamic path, was bizarre. But it turned out this was the bridge. It linked gravity, quantum mechanics, and thermodynamics into a tantalizing triangle. Each side hates the other two, but together they might describe the full machinery of the universe. Emphasis on might. Historians still argue whether this triangle holds, or if we're just squinting too hard at chalkboards. Here's a quirky detour for you. Before Hawking, physicists like John Wheeler used to talk about black holes as having no hair. That meant black holes were completely described by only three things: mass, charge, and angular momentum. No other features, no extra fluff, just bald, hungry geometry. But if black holes have temperature, then maybe they have microstates, tiny, hidden configurations that store information. And if that's true, maybe they're not bald after all. Maybe they've got a toupee of secrets. At this point, your proximity alarms chirp. Probably wise. The event horizon is still out of reach, but its gravitational pull is palpable. If you shut off your engines, you'd be toast in seconds. You feel the pressure of the space-time curvature, your atoms subtly stretched and compressed in ways you're not supposed to notice. And yet, the black hole just sits there, perfectly calm. From the outside, nothing seems to happen. No rumbling, no visible change, no Hollywood implosions. But now you know the truth. It's dying. Slowly. Icy cold to the touch, but mathematically feverish inside. For a fun fringe fact, in 2005, researchers created an artificial event horizon in a laboratory using sound waves in a Bose-Einstein condensate. They even claimed to detect a sort of Hawking-like radiation. Not light, but phonons, quantized sound particles. Black holes may be silent, but their analogues can hum. You glance at your heat sensors one last time. They're still reading near zero values, but not zero. That's the key. Not absolute nothing. Just the faintest trace of something, of temperature, of loss, of decay. A black hole with a temperature is like a furnace that runs on silence, a heater that only works when you look away. It doesn't warm the room, but it keeps the laws of the universe from unraveling completely. Probably. So what have we learned while staring into the abyss? That even nothingness isn't free from accounting, that the void still gets a thermal invoice every trillion years or so, and that you, lucky stargazer, are now officially warmer than a stellar mass black hole. Congrats. Try not to get cocky about it. You keep your craft steady, orbiting just outside the black hole's event horizon, where physics teeters between somewhat understandable and dream logic. It's here, in this no man's land of space-time, that one of the most quietly profound things about black holes starts to reveal itself: entropy. Let's start with the basics, but very softly. Entropy is the measure of disorder in a system. It's the reason your room tends to get messy, and why you can't stir cream out of coffee once it's blended in. Entropy always increases in an isolated system, and black holes, surprisingly, follow this rule too. But here's the first twist that'll gently tickle your brain like a feather dipped in math. Black hole entropy doesn't live inside the hole. It lives on the event horizon, the surface, the skin, not the volume. You lean closer, metaphorically, and feel it. This strange, ghostly skin that defines the black hole's boundary. It's not a physical shell, but a kind of conceptual surface, and it's hiding an enormous amount of information. If you measure the area of this surface in Planck units, the tiniest measurable bits of space, you find that the entropy of a black hole is proportional to that area. Not its depth, not its content, just the shell. Why is that weird? Because normally, entropy scales with volume. A gas in a container has entropy based on the number of molecules bouncing around inside, not how shiny the jar is. But black holes, they break the mold. They're entropy hipsters. This concept was first explored seriously by Jacob Bekenstein. Yes, the same guy we mentioned earlier, the one with the messy thermodynamic closet. He suggested that when you throw stuff into a black hole, its surface area increases in a way that mimics how entropy increases in regular thermodynamic systems. It was a gutsy claim, especially in the early 70s, when most people still thought black holes were just the universe's very serious garbage disposals. Historians still argue whether Bekenstein was being bold or just lucky. But when Hawking came along and confirmed his ideas with the radiation calculations, the physics community took a collective step back and said, wait a minute. Now entropy was no longer the exclusive domain of steam engines and broken eggs. It was somehow encoded into the boundary of space-time itself. You let this sink in, staring at the event horizon like it's a very, very old book, one whose pages have been burnt but whose cover still holds a record of the story. This brings us to the so-called Bekenstein-Hawking entropy formula, S equals Ka over 4hg, where S is entropy, A is the area of the event horizon, and the other symbols are familiar constants. K is Boltzmann's constant, H bar is the reduced Planck constant, and G is the gravitational constant. Again, no math test here. Just marvel at how simple it looks. Suspiciously simple, like the kind of equation that makes physicists both giddy and afraid. You probably feel a tingle of recognition here. If entropy lives on a surface, and not in a volume, that sounds awfully familiar. Yep, that's the whisper of the holographic principle in the distance, though we'll spend more time with that later. For now, just know that this surface-based entropy changed everything. Let's take a quick sensory detour. Imagine the event horizon as a membrane, not a real one, but a metaphorical film stretched over the black hole. Every bit of area corresponds to a unit of entropy. That means as more mass falls in, the surface grows, and the entropy increases. Black holes don't just get heavier, they get messier in a very abstract bookkeeping sense. Now here's a charmingly bizarre fringe fact. Some physicists think the event horizon might be made up of tiny quantum bits, like pixels on a screen but for space-time. Each pixel carries a sliver of entropy. You're basically floating next to the universe's most compact data storage system. No USB port though. Sorry. And here comes your historical fix for the night. Back in 1971, Stephen Hawking proved a fascinating theorem. The total area of black hole event horizons in the universe can never decrease. It's a little like the second law of thermodynamics. Entropy never decreases, except this one applies to black holes. But wait, you're thinking, didn't you just say that black holes evaporate via Hawking radiation? Shouldn't the event horizon shrink? Exactly. That's where things get deliciously complicated. Hawking's area theorem only holds if quantum effects are ignored. But once you add quantum mechanics, everything wobbles. The event horizon can shrink. So, do black holes break the second law of thermodynamics? Not quite. Because even though the black hole's entropy goes down during evaporation, the radiation it emits carries entropy too. In fact, calculations show that the total entropy of the universe still goes up. The house still gets messier, even if one room is vanishing. Physicists continue to debate whether the entropy of a black hole truly reflects hidden microstates, real, countable bits of information, or whether it's just a statistical trick. You'll hear phrases like emergent gravity or entropic gravity whispered in conference halls, always with a hopeful shrug. But whether you take the theory literally or metaphorically, the entropy is there. It obeys laws, it evolves, it glows with thermodynamic purpose. And you hover at the boundary of understanding, watching the equations pulse softly on your display. In the end, entropy is the universe's memory of change, and a black hole is the most secretive librarian imaginable, one that keeps the memory on its outer shell locked in a language we barely understand. You're starting to see it now, the quiet genius of black hole thermodynamics. This isn't just about stars collapsing or space getting weird. This is about the universe whispering, through equations and radiation, that even the deepest silences must obey the laws of heat. And as you orbit the horizon, you swear, just for a second, you feel that heat brushing past your senses. Not much, just a shiver. You float there, sensors blinking dimly, wrapped in the cold hush of interstellar space, and yet, your mind keeps drifting back to that flickering ember of theoretical warmth. Somewhere beneath the chill of space and the utter stillness of a black hole's shadow, Stephen Hawking once struck a match. Cambridge, 1974, the kind of rainy British afternoon that makes you question whether the sun ever existed. Inside a cramped office stacked with papers and equations like firewood, Hawking stared at a problem that refused to sit quietly. Black holes, he believed, were more than just gravitational vacuum cleaners. They were quantum mischief makers. This is the part where reality began to unravel. See, Hawking wasn't even trying to prove black holes radiate. He was working on a completely different problem. What happens to quantum fields near a black hole? The idea was to apply quantum field theory, how particles behave in empty space, to a curved space-time background. In simpler terms, what happens to nothing when gravity's cranked to 11? And out of this came something Hawking didn't expect. His calculations showed that the vacuum near the event horizon wasn't as empty as it looked. Thanks to the uncertainty principle, our old friend from quantum mechanics, particles are constantly popping into and out of existence. These virtual particles usually cancel each other out in an instant, like two actors who forget their lines and exit stage left. But near a black hole, something bizarre happens. If a virtual particle pair forms right on the edge of the event horizon, gravity can split them. One falls in, the other escapes. And because the escaping particle wasn't supposed to exist, the universe does some quick cosmic bookkeeping. It subtracts that energy from the black hole, which means slowly, very slowly, the black hole loses mass. The result? Hawking radiation. It was like discovering a hole in the laws of physics that lets light slip out from behind the curtain, and it meant something staggering. Black holes are not eternal, they die. Eventually they vanish in a puff of particles, their immense darkness swallowed not by more gravity, but by heat. You sit with that. Imagine a black hole the mass of our sun, immense, terrifying, ancient. According to Hawking's equations, it would take more than 10 to the power of 67 years for it to fully evaporate. That's about 1,000,000 trillion times the current age of the universe, give or take a millennium, but the mechanism is there, and more importantly, it changed everything. Before Hawking's insight, black holes were thought to be one-way streets. What went in never came out. They were the cosmic delete key, but now they leak, they have temperature, they radiate, and for that to happen, they must have entropy. This was the spark that lit the bonfire of black hole thermodynamics. Remember Bekenstein's controversial claim that black holes had entropy? Before Hawking, it was just a clever guess, but once the radiation was proven, that entropy needed to be real. Otherwise, the thermodynamic story wouldn't add up. You can't have temperature without entropy. That's like trying to have a fever without symptoms. And so, Hawking and Bekenstein became the reluctant parents of a strange new science, a mashup of quantum mechanics, relativity and thermodynamics, with black holes as the centerpieces. Even Einstein never saw this coming. Here's a lovely historical tidbit for you. Hawking initially bet against the idea that information could escape a black hole. He famously made a wager with physicist Kip Thorne that information was truly lost forever once it crossed the event horizon. It wasn't until decades later, that Hawking admitted he'd been wrong. At a conference in 2004, he publicly conceded and handed over a baseball encyclopedia as the prize. Because physics is petty and poetic, historians still argue whether Hawking's radiation theory has been conclusively proven. After all, it's not like we can hover near a black hole for a few trillion years and check. But the theory remains our best window into how gravity and quantum mechanics might play together. Awkwardly, like middle schoolers forced into a square dance. You gaze out the viewport again, imagining the ghost of radiation washing past you, too faint to feel but ever present. That's what Hawking saw in the math. The silence wasn't silent, the black wasn't entirely black. And that brings us to the most beautifully cursed part of the theory. The black hole evaporates, not explodes, not collapses further. It just loses mass, little by little, like a campfire dwindling into ash. But the smaller it gets, the hotter it becomes. Remember our inverse relationship? As mass goes down, temperature goes up. So near the end, the process speeds up, a runaway thermal death spiral. And when the mass reaches a certain threshold, close to the Planck mass, things get really weird. Theories diverge, quantum gravity takes over, and we no longer know what happens. Some say the black hole simply vanishes, others think it leaves behind a stable remnant. A few rogue theorists suggest it might trigger a baby universe. That's right, an entire new cosmos birthed from the death rattle of a black hole. But no one knows. That's part of the magic. Hawking's bonfire is still burning somewhere in the math, and as you drift here, on the edge of this impossible object, you feel it too. The heat that shouldn't exist, the particles that shouldn't escape, the slow leak that turns giants into whispers, and maybe, just maybe, This is where physics stops being a science and becomes something closer to poetry. You're watching entropy unravel the ununravelable. You're seeing time itself impose a countdown on something once thought immortal. A black hole isn't just an ending, it's a process. And as Stephen Hawking quietly rewrote the rules in that rainy Cambridge office, the universe tilted just a bit. Enough for the coldest, darkest thing we know to start warming up. You're still orbiting the abyss, floating, humming, very much intact. But your thoughts are now stuck on a simple geometric riddle. Why does a black hole's entropy depend on area and not volume? It doesn't make intuitive sense. Everything else in your life obeys the logic of bulk. The more stuff inside a thing, the more disorder it can have. A box of marbles, a room full of bouncing gas molecules, your hard drive full of questionable downloads. It's all about how much you can cram inside. But a black hole, it keeps its secrets on the surface. This is the area law, the idea that the entropy of a black hole scales with the area of its event horizon, not its internal volume. That's like saying your house's messiness depends not on how many rooms you have, but on the square footage of your windows. And yet, when you do the math, it works. Over and over again. You drift closer to the shimmering, not quite visible edge, thinking about what that really means. Every square Planck unit of the event horizon, a length so tiny it's effectively the pixel size of the universe, contains one bit of information. One piece of whatever was lost inside. One quantum mark on the record. If black holes have entropy, and entropy counts microstates, tiny possible configurations, then where are these states hiding? Certainly not inside. You can't even define inside without time falling apart. So, all those lost details must live on the horizon, like footprints on a doormat. You run a sensor sweep, nothing unusual. No glow, no signal, just a silent, invisible curtain. And yet, it's the most information-rich surface in the known cosmos. Now here's where things get rude. The area law seems to violate everything we expect from how entropy should work. In thermodynamics, entropy is extensive. It scales with volume. But in black holes, it's holographic. It lives on a surface. Historians still argue whether this is a unique quirk of gravity, or a clue that all of spacetime is fundamentally two-dimensional, with the third dimension being some kind of illusion. A projection, like a 3D movie on a 2D screen. You probably didn't come here tonight expecting your reality to get pancaked, but here we are. Back in the 1970s and 80s, when physicists started seriously entertaining this area surface weirdness, the implications began to pile up. Could it be that all physical systems, everything, are actually encoded at their boundaries? Could the universe itself be one giant hologram? That's for later. For now, just savor how calmly black holes break all your spatial assumptions. You toss something in, a coffee mug, a cat, your entire tax history, and the black hole grows. But it only grows in surface area. That's where the entropy is tallied. That's where the change happens. Here's a quirky, often overlooked tidbit. There's something called the generalized second law. It says that the total entropy of the universe, including the entropy of black holes, must never decrease. So when you drop your late-night snack into a black hole, the loss of entropy from the snack is more than made up for by the increase in the hole's surface area. The universe still gets messier. It's comforting, really. But wait, doesn't that mean black holes absorb entropy? Isn't that suspiciously convenient? Like a universal rug to sweep your thermodynamic crimes under? Yes, and that convenience is exactly what makes black holes useful. They became perfect thought experiments. You could test the laws of thermodynamics, of information, of entropy, just by imagining what happens when something crosses the horizon. And what you'd find is that the whole always balances the books, always, unless it doesn't. There's one dangerous edge case, and we might as well lean into it. You imagine a scenario where two black holes merge. The resulting black hole has a new event horizon, one that's larger than the sum of the two originals. That fits the area law. Entropy increases. But now imagine an advanced civilization, somewhere between Type 2 and Type 3 on the Kardashev scale, figures out how to engineer entropy. What happens if they somehow reverse the evaporation? Could the surface area decrease? Could the entropy fall? So far, all attempts to violate the generalized second law have failed. Even the sneakiest Gedanken experiments. Yes, that's German for thought experiments because physics always sounds better when it's brooding. Preserve the total entropy, one way or another. This might be why so many physicists treat black holes with such reverence. They aren't just astrophysical oddities, they're the final exam for every physical law we think we understand. If something breaks down here, it's broken everywhere. Let's pivot to a sensory thought. You glide your hand, not literally, because that would be insane, along the surface of the event horizon. You imagine your fingers tingling with the data encoded there. Bits of crushed stars, stretched time, scrambled atoms, the ghost memories of everything that ever fell in, now reduced to quantum graffiti. And yes, we're personifying physics again. It helps. The strange part is this. The event horizon doesn't do anything technically. It's not a solid surface. You could cross it without noticing, assuming you ignored the tidal forces, which you shouldn't. But in terms of information, that horizon is the record, the scoreboard, the heat ledger. You think of it like a cosmic skin, an interface between what you know and what you'll never know again. Everything that goes past it is not just lost physically, but smeared across that horizon in some unfathomable thermal code. And just to twist the knife, once the black hole finishes evaporating, that horizon vanishes. So where does the information go then? That's the information paradox. We'll get to it. It haunts physicists like a phone that keeps buzzing in their dreams. But for now, you just sit back, admiring the elegant contradiction. The most empty thing in the universe has the most information. The most frozen thing burns. The surface of nothing is filled with everything. The area law might be a lie, but only in the way that all the best truths are. Temporarily, helpfully, wildly strange. You hover in silence, orbiting the void, but now your mind's eye is rummaging through the theoretical attic of one very particular physicist, Jacob Bekenstein. It's dusty in here, equations scattered everywhere, concepts balanced precariously on top of each other like old pizza boxes, and in the corner, a strange little idea, thermodynamics, but for black holes. You drift closer to the memory of Bekenstein himself, young, sharp, bold in a way that probably annoyed his professors. It was the early 1970s, and he'd just proposed something that made many physicists tilt their heads like confused owls, that black holes had entropy. Real, measurable entropy. A thermodynamic quantity, not just some math trick. He basically asked, what if we treat this infinite cosmic mystery like a really, really slow coffee maker? But the idea didn't land gently. Why? Because black holes were supposed to be simple, as in no-hair theorem simple. They were defined entirely by mass, charge, and angular momentum. Nothing else. No microscopic structure, no secrets, no thermodynamic shenanigans. Yet here was Bekenstein, saying that if you dropped a cup of tea, or a physics textbook, or a memory, or your neighbour's annoying poodle, into a black hole, the entropy had to go somewhere. Otherwise the second law of thermodynamics would break, and physics, for all its cosmic drama, hates broken laws. At the time, most people thought he was being metaphorical. Surely this was just a clever analogy, a thought experiment, not a literal claim. But Bekenstein was serious. He believed that black holes must obey thermodynamic rules, that the event horizon's surface area wasn't just geometry, it was physical, it meant something. So he started digging. He calculated how much the surface area would increase when matter fell in. He compared it to how much entropy the matter had before it vanished. And he found something astonishing. The area always increased at least enough to cover the incoming entropy, which meant the horizon was keeping score, and just like that, black holes got messy. Here's a cheeky fringe detail. Bekenstein originally proposed that a black hole's entropy was proportional to the logarithm of the number of internal microstates. That's actually pretty standard in statistical mechanics. The twist was that he suggested this formula would apply to the surface area of the horizon, not the volume. Once again, that upside-down logic we're learning to love. Now, Bekenstein didn't have all the pieces. He didn't know about Hawking radiation yet. That bombshell was still smouldering on Stephen Hawking's chalkboard across the Atlantic. But Bekenstein's work laid the theoretical tracks that Hawking's train would eventually thunder down. When Hawking's radiation paper came out, it vindicated Bekenstein completely. Suddenly, the entropy had to be real. If black holes radiated like thermal objects, then they needed all the trappings of thermal physics, temperature, entropy, energy exchange, the whole messy kitchen. And just like that, Bekenstein's dusty thermodynamic closet swung wide open. Inside, you find a curious connection between entropy and information. Bekenstein argued that entropy wasn't just disorder, it was also a measure of how much you didn't know. In the black hole context, that was terrifyingly literal. Everything that fell in, gone, unknowable, but its existence still affected the black hole's surface area. Its entropy left a scar, even if its shape didn't survive. Historians still argue whether Bekenstein fully understood the depth of this insight. Some say he stumbled into something profound. Others believe he saw the whole iceberg beneath the tip. Either way, the shift was seismic. Entropy now lived on the edge of the abyss. You drift beside the event horizon, and you start to appreciate its role. It's not just the point of no return, it's a ledger, a boundary where thermodynamics and gravity co-sign the universe's strangest receipts. You can't help but think of it like a library checkout system from hell. You drop something in. The black hole doesn't tell you what it took, but it changes the number of books in the vault. No titles, no pages, just a growing surface that insists, yes, something was borrowed. Here's a playful but surprisingly accurate analogy physicists have used. The event horizon behaves like a kind of stretched membrane, complete with viscosity, conductivity, and thermal properties. They call it the membrane paradigm. Imagine a soap bubble stretched over the black hole, one that jiggles, vibrates, and heats up as the universe pokes it. A surface that acts like a system in its own right, even though it's not real in the usual sense. It's like the universe built a fake surface just to keep the laws of thermodynamics happy, for appearances. And Bekenstein's closet, now overflowing with strange ideas, becomes a kind of origin point for black hole thermodynamics as a real field. His arguments, risky at the time, forced physicists to confront a horrible question. What does it mean when gravity has entropy? It was easier when gravity was just geometry, when space bent around stars and everyone nodded politely. But now gravity was participating in statistical mechanics. It had heat, disorder, maybe even microscopic building blocks. That hint, just a whisper of microscopic structure, was enough to awaken even deeper questions. If black holes had entropy, did they also have microstates? Were there quantum bits hidden in the space-time fabric? Could gravity itself be emergent, just a statistical byproduct of deeper laws? This was the beginning of the modern age of quantum gravity research, and you're hovering at the edge of it, watching the strange ripples of thermodynamic reasoning spread outward from Bekenstein's bold proposal. One last quirky note, Bekenstein also tried to set an upper bound on how much information could be stored in a given region of space. This became known as the Bekenstein bound, and it tells us that the maximum amount of information is not determined by volume but by surface area. Sound familiar? Yep. It's another breadcrumb on the trail to the holographic principle, but more on that soon. For now, you're floating in the shadow of a man who stuffed entropy into a black hole and made physics groan under the weight of the implications. That messy thermodynamic closet, it's still open, and it's full of surprises. You give the thrusters a delicate nudge, nudging your craft into a perfectly balanced hover just above the event horizon, still safely on the outside, of course, unless you're in the mood for an extremely one-way adventure. It's time to step back from the drama and entropy debates, and finally simmer down to the most basic model of a black hole, the Schwarzschild black hole. Ah yes, the plain bagel of black holes, no spin, no charge, no toppings, just mass and gravity, sitting there like the cosmic equivalent of a concrete floor. But as bland as it may sound, this flavourless singularity is the foundation of everything that follows. You've probably seen the word Schwarzschild on a half-dozen physics infographics, and immediately scrolled past it because it looked like a sneeze in German. Let's give it a proper moment in the sleepy spotlight. The Schwarzschild solution is the very first exact solution to Einstein's field equations, published in 1916 by Karl Schwarzschild himself. Fun fact, he derived it while serving in the German army during World War I, just casually solving the fabric of the universe between artillery shellings. Because physics waits for no one, this solution describes the space-time geometry around a non-rotating, uncharged, spherically symmetric mass. That's a mouthful, but the takeaway is this. It's what you get when you squash a star into a point with no flare. The simplest black hole imaginable. And in this simplicity lies its terrifying elegance. You watch the geometry shift as you simulate approaching the Schwarzschild radius, the critical distance from the centre of mass at which the escape velocity equals the speed of a light. Go any closer, and not even light can escape. This is the event horizon, the point of no return. You're not at the singularity yet. Goodness no, that's buried inside. But once you cross the horizon, everything you know about forward becomes down. So how does heat factor in? Here's where the Schwarzschild black hole surprises you. It radiates, slowly, reluctantly, but it does. Thanks to Hawking radiation, this simplest of black holes isn't truly silent. It's whispering energy into space at a glacial pace. Let's plug in some real numbers. Don't worry, we'll keep it PG-13. A Schwarzschild black hole with the mass of the Sun has a temperature of about 60 nanokelvin. That's colder than the cosmic microwave background, which means it absorbs more radiation than it emits. It's not until black holes get much smaller, say asteroid-sized, that the temperature rises enough for evaporation to outpace absorption. You float closer to your simulated mini Schwarzschild, this one no bigger than a mountain, and now the radiation becomes real. The temperature climbs into measurable territory. You can almost feel the ghost heat brushing your senses. The black hole starts to act like a furnace, albeit one so energy-starved it's barely flickering. What's the entropy here? You've got the formula from earlier, S equals A divided by 4 in Planck units. For a Schwarzschild black hole, that area is easy to calculate. It's just the area of a sphere with radius equal to the Schwarzschild radius. And since that radius depends only on mass, the entropy does too. Larger black holes, more entropy, more surface area, more information stored in the void. Now here's where things get beautifully dumb. The entropy of a Schwarzschild black hole is staggeringly large, like you could store the entire internet in a thimble large. A stellar mass black hole has about 10 to the 77th power bits of entropy. That's more than all the matter in the known universe could ever encode, and yet it does absolutely nothing with it. It just sits there. There's something almost comical about that. You've got the most efficient data storage object in the universe, and it's just yawning into the vacuum, slowly losing mass one photon at a time. Maybe it's the ultimate hard drive, and we just haven't figured out how to read it yet. Or maybe it's cosmic irony in its purest form. A quirky historical sidebar. The Schwarzschild metric contains a coordinate singularity at the event horizon. Early physicists thought it was a physical singularity, like space-time actually broke there. But later coordinate transformations, like Kruskal-Sekaros coordinates, showed it was just a trick of the math, a removable inconvenience, like peeling the do not eat label off a silica packet and realizing it's still not food. What's not removable is the singularity at the center. That's the real deal. A true breakdown of physics where curvature becomes infinite. And yet, the temperature we measure from outside, the Hawking temperature, depends only on the surface, not the center. It's like judging a microwave's heat by staring at the door. You circle the Schwarzschild model again, noticing how incredibly clean it is. There's no magnetic field, no swirling jets, no rotation, just gravitational collapse in its most pristine form. And yet, even here, thermodynamics creeps in. Even this sterile void follows the rules of heat. Here's a fun fringe twist. Some theoretical physicists have tried to simulate Schwarzschild black holes in lab conditions. Not with mass, obviously, but using analog systems, fluids, optical fibers, and even Bose-Einstein condensates. These analog horizons have produced radiation that behaves suspiciously like Hawking radiation. The implication? Black holes may not be special. Their thermal behavior might be a deeper, more universal feature of nature. Historians still argue whether these lab setups actually prove anything about real black holes, but the mere fact that you can fake a Schwarzschild horizon using glass and a laser suggests something powerful. The math of black holes, stripped of its astrophysical drama, still points to the same thermodynamic truths. And now a tiny speculative whisper in your earpiece. If black holes can be boiled down to such clean thermodynamic objects, are we looking at a real physical system, or just a metaphor? Is the Schwarzschild solution a description of a physical entity, or a hologram of something deeper? You hover, drifting silently, watching the simplest of black holes emit the faintest of radiation. No spin, no charge, just mass and temperature, tied together in a dance that stretches time, flattens space, and somehow, against all odds, follows the rules of heat. You didn't expect it, but now you see, even the plain bagel is toasted. You shift your course just slightly, allowing your vessel to curve into a new trajectory, one that brings you around a different kind of monster. If the Schwarzschild black hole is the blank canvas, then what you're staring at now is the dizzying spin art version. This is a Kerr black hole, a rotating black hole, and it's not here to play nice. You immediately feel the difference. Space doesn't just fall inward here, it twists. The rotation drags space-time around with it, a phenomenon known as frame dragging. If you tried to hover near the event horizon without moving, you'd fail. Space itself is rotating so fast that you're forced to move with it, like getting caught in a slow-motion whirlpool made of geometry. This swirling zone around the black hole is called the ergosphere, and yes, it sounds like a retrofuturist exercise machine. But in reality, it's a region just outside the event horizon where no object can remain stationary, not even light. Unlike the event horizon, you can escape from the ergosphere if you work hard enough. But while you're in it, the black hole's rotation spins the rules of motion like a blender with boundary issues. So what happens to temperature when you add spin? Let's recap. Hawking radiation depends on the surface gravity of the black hole, the force that would be needed to hover just above the event horizon. For a Kerr black hole, this surface gravity changes with rotation. In fact, the faster the spin, the lower the surface gravity, and thus the lower the Hawking temperature. So yes, spinning black holes are cooler, literally. A maximally rotating Kerr black hole, the fastest spin allowed by physics, would radiate less than a Schwarzschild black hole of the same mass. It's as if spinning helps the black hole conserve its heat, stretching the thermodynamic clock even further. You drift toward the outer edge of the ergosphere, sensors trembling just slightly, as the gravitational equations around you start to twist into corkscrews. This region is weirdly useful. Thanks to that spin, you can actually extract energy from the black hole. This isn't just theory, it's a concept known as the Penrose process. Named after Roger Penrose, who also gave us some of the most confusing tiling patterns known to man, this process involves sending a particle into the ergosphere. If the particle splits in just the right way, one half falling in, the other escaping, the escaping piece can actually come out with more energy than the original had. The black hole loses a bit of its rotational energy, and you gain a cosmic boost. This idea became the foundation for various energy extraction theories, including some extremely speculative black hole power plants you've probably seen in late-night sci-fi forums. Technically possible, practically ridiculous. But still, physics doesn't say no, and in a thermodynamic sense, the Penrose process resembles a kind of engine, an energy cycle based on the black hole's spin. In fact, you can think of a rotating black hole as a heat engine, converting angular momentum into usable energy before it lazily leaks its mass away via Hawking radiation. Historians still argue whether the Penrose process counts as a true thermodynamic cycle, or if it's just a clever energy hack. Either way, it highlights a key fact. Rotation adds complexity. It gives the black hole an extra handle for entropy to grab onto. Let's talk entropy now. For Kerr black holes, entropy still follows the area law, but the area of the event horizon is altered by spin. A rotating black hole has a smaller horizon than a non-rotating one of the same mass. Less surface area equals less entropy, which makes sense. Adding structure to the system typically reduces randomness. But here's the real kicker. Kerr black holes are stable against Hawking radiation until they lose some of their spin. The spin acts like an entropy shield, lowering the rate of evaporation. It's only when they slow down that the temperature rises and the black hole begins its slow fade into heat death. Picture it this way. Spin is like a blanket, insulating the black hole against thermal loss. As it unravels, the cold creeps in. Let's throw in a fringe fact to keep your mind busy. In 2020, astronomers detected a possible echo in the gravitational wave data from a black hole merger. Some researchers speculated it could be evidence of quantum fuzz near the event horizon, something Kerr black holes, with their added complexity, might reveal more readily. Still unconfirmed, still whispered about, but intriguing. You orbit now in a tilted loop, letting the visualizer overlay the spinning horizon with false color gradients of entropy. The numbers swirl. The entropy here is less than in a Schwarzschild hole, but the structure is richer. It's a little like comparing a messy attic to a high-tech filing system. Same mass, different vibes. And there's one more oddity. Inside a Kerr black hole, if you dared to enter, you wouldn't immediately hit the singularity. Instead, you'd enter a region with closed time-like curves. Yes, time loops. You could, in theory, travel along a path that takes you back to your own past. Not that you'd survive the trip, but the math permits it. Barely. Do rotating black holes rewrite the timeline of thermodynamics? Maybe not. But they do stretch it. Spin adds degrees of freedom. It adds ways for the black hole to store energy, manipulate entropy, and delay its own thermal endgame. And so you drift alongside it, this spinning furnace of impossible gravity, this cosmic pirouette in a vacuum. You can't hear it, can't touch it. But its angular momentum leaves fingerprints on the surrounding space-time, and in the far, far future, after trillions of years of evaporation, what remains? A black hole that spins more slowly, that grows hotter, that radiates more eagerly. And finally, like all the others, it vanishes. Not with a bang, but with a whisper of heat. One last photon, one last shiver, one last ember from the universe's slow-burning core. You ease your vessel into a new orbit, just a hair wider this time. You've studied black holes without spin, and black holes that spin like record players. Now, you're approaching a different beast entirely. It hums with electricity, it's charged, it's weird, and it's called a Reissner-Nordström black hole, the kind that would fry your ship long before gravity got its claws into you. This is the least socially adjusted black hole in the trio. You know how normal black holes suck in matter and quietly warp space-time? Not this one. It also exerts electrostatic force, a sort of gravitational buzz with a side of high-voltage spice. It's the black hole equivalent of licking a 9-volt battery while free-falling into a well. Named after Hans Reissner and Gunnar Nordström, this solution to Einstein's equations describes a non-rotating black hole with electric charge. It was developed not long after Schwarzschild's work, back when general relativity was still the new kid at school. And here's where the drama kicks in. Reissner-Nordström black holes don't just have one event horizon, they have two. One outer horizon, the one you'd usually call the point of no return, and an inner horizon deeper inside called the Cauchy horizon. Between them lies a zone of maximum chaos, where determinism goes to get a drink and cry in the corner. Your ship's sensors ping softly as you model the gravitational and electromagnetic forces. The field around a charged black hole doesn't just bend space-time, it warps the very notion of what in and out mean. Light curves, particles jitter, and anyone without proper shielding would experience a full-body electric sizzle before getting anywhere near the horizon. Now you're wondering, can real black holes be charged? Technically, yes. But not for long. In nature, black holes are expected to shed their charge quickly. Why? Because the universe is stuffed with plasma. Any charged black hole would immediately attract opposite charges from its surroundings, neutralizing itself in a cosmic version of opposites attract. So while Reissner-Nordström black holes are mathematically pristine, they're probably unicorns in real life, rare, brief, and a bit smug about it. Still, they're a crucial part of our black hole thermodynamics toolkit. Let's talk about their temperature. Here's the twist. The more charge a black hole has, the cooler it gets. At full charge, what we call the extremal limit, the black hole's temperature drops to 0. That's right, absolute 0. No Hawking radiation, no slow death, just a silent frozen monolith humming with electrostatic defiance. At this extremal point, the inner and outer horizons merge, creating a bizarre structure where time, space, and thermodynamic laws all shrug in unison and say, we're not sure either. You lean into the math. The surface gravity, which determines Hawking temperature, diminishes as the charge approaches this maximum. In the extremal case, surface gravity vanishes, and so does the radiation. A black hole that doesn't radiate, that's a pretty big problem for the whole black holes evaporate story. Historians still argue whether extremal black holes are real physical entities or just mathematical artifacts. If they exist, they might never evaporate. They'd be thermodynamic zombies, undead, unmoving, but forever storing entropy with no intention of letting it go. Entropy, by the way, still exists in a charged black hole, but just like with the Kerr model, it's trickier. The area of the event horizon, and thus the entropy, is modified by the presence of charge. The formula stretches, taking on a few extra terms to accommodate the electromagnetic field. Entropy still scales with area, but the horizon is altered. And here's something wildly fringe. Some string theorists believe extremal charged black holes might help us count their microstates, The reason? Because their zero temperature freezes things in place, making the quantum math cleaner, more countable, easier to work with, which is why extremal black holes keep showing up in string theory papers like party guests who brought their own equations. Now, let's look inside. Once you fall past the outer event horizon of a Reissner-Nordström black hole, you pass into the region between horizons. Here, time and space flip roles in weird and specific ways. The singularity isn't just a point, it's a time-like one. That means it lies in your future, not your location. You're being dragged toward it, not because of where it is, but because of when it is. Then you cross the inner horizon, the Cauchy horizon, and everything gets weird. According to the equations, if you could somehow pass this boundary without being ripped apart, you'd enter a new region of space-time, maybe even another universe. The Reissner-Nordström solution is mathematically extendable, meaning you could, in theory, leave this black hole into another one. This is the black hole version of a back door, or a tunnel, or a very untrustworthy elevator. But here's the kicker. The Cauchy horizon may not be stable. Tiny perturbations, ripples in the field, quantum fuzz, anything, could trigger a catastrophic explosion of energy as you approach. This is called mass inflation, and it's just as pleasant as it sounds, so you probably won't be touring the multiverse anytime soon. Still, this idea of multiple horizons and alternate pathways gives us a hint. Black holes aren't just thermal blobs, they're layered, structured. Their temperature and entropy aren't static. They evolve depending on spin, charge, and how close you get to the edge. A Reissner-Nordström black hole is like an onion of confusion. Each layer reveals a new flavour of thermodynamic discomfort. And one last spooky fact before you coast away. Reissner-Nordström black holes challenge the cosmic censorship hypothesis, the idea that singularities are always hidden behind horizons. In some charge configurations, if you overcharge a black hole, in theory, the event horizon disappears entirely, revealing a naked singularity. That's the ultimate physics party foul. No one's sure if nature allows it. The laws of physics get cagey, the equations blush, and your sanity? Probably evaporated faster than the black hole ever could. But here's what we do know. Charge changes everything. It lowers temperature, it warps horizons, it reshapes entropy, and in doing so, it adds one more layer to the riddle of black hole thermodynamics. You drift away now, sensors cooling off, letting the charged beast recede behind you. No explosions, no flashes, just a silent, buzzing orb of stored energy and frozen potential. A black hole that could live forever, or collapse tomorrow, depending on who's asking the questions. You ease into a slow coasting orbit, far enough now to take in the black hole as a whole, not just the furious details around its edges, but something's tugging at your attention. Not gravity, not charge, not spin. No, it's something even stranger. Light, or rather, the lack of it. And then, paradoxically, its faint return. You've reached the point in your long, sleepy descent where it's time to really reckon with the thing that made this all possible. Hawking radiation. The idea that black holes leak. That even the most perfectly black object in the universe can't hold on to its secrets forever. You stare into the darkness. It's not glowing in any traditional sense. But mathematically, oh, it's glowing. Leaking. Dying. Slowly and thermally, like a candle that was lit before atoms even formed. Let's back up and talk about how. In quantum field theory, even empty space is never truly empty. There's a jitter to the vacuum, an endless fizz of virtual particles flickering into existence, then annihilating before anyone can catch them in the act. Normally, these pairs appear and disappear together, with no observable effect. But a black hole, rude as ever, interrupts that dance. At the event horizon, gravity bends space-time so sharply that when one virtual particle pair appears near the edge, one half may fall in, while the other escapes. The one that escapes becomes real, an actual detectable particle flying off into the universe, and its partner, trapped inside, carries negative energy relative to the outside world. It subtracts from the black hole's mass. Every escaping particle is a tiny bite out of the black hole's energy. This, in essence, is Hawking radiation. You can almost visualize it now, like tiny flickers of heat rising from the edge of the void, a ghost campfire smouldering in the mathematical distance. No sound, no light you can see, just a steady, unyielding tick-tick-tick of entropy unwinding. And now you remember, Black holes aren't cold just because they're black. They're cold because they radiate, and anything that radiates has a temperature. That was Hawking's incredible leap. He took the most frigid object in the known universe and gave it a fever. But don't get too excited. The temperature of this radiation depends inversely on the mass of the black hole. The bigger the black hole, the cooler it is. A stellar mass black hole, the kind left behind by collapsed stars, has a temperature of mere nanokelvins. That's colder than the cosmic microwave background. So paradoxically, these black holes are still gaining mass from the ambient radiation around them. Only when they shrink down, through hypothetical slow evaporation, do they begin to emit more than they absorb. Then their temperature rises, and as they continue to shrink, they radiate faster and get hotter. Until finally, at the very end, the black hole evaporates in a blaze of fury, an outburst of light, energy, and possibly particles we've never seen before, the final gasp. Historians still argue whether this final moment actually exists. Some think the black hole leaves behind a Planck-scale remnant, a tiny, stable object that refuses to go quietly. Others suggest a final burst of radiation that contains all the lost information, like a dying star vomiting up its secrets in one last gasp. And here we stumble directly into the heart of the black hole information paradox. Here's the issue. If black holes radiate thermally, like black bodies, then that radiation contains no information about what fell in. It's just noise, random, featureless thermal soup. But that violates a core principle of quantum mechanics. That information can't be destroyed. You can't unwrite the universe's diary no matter how hard you try. Even if you burn it, the ashes still encode the story, if you could only reconstruct it. But black holes, they seem to burn it and erase the ashes too. So where does the information go? This question, born from Hawking radiation, has haunted physicists for decades. It's not just a technicality, it's a foundational crisis. If black holes truly destroy information, then quantum mechanics isn't complete. Or worse, wrong. Some theories suggest the information is encoded in the Hawking radiation itself, just in a highly scrambled form. Others propose that the event horizon is a kind of storage device, a cosmic flash drive encoding every detail of what fell in. Still others claim that quantum entanglement somehow preserves it in a form we can't yet decode. The truth? We don't know, but we do know this. Hawking radiation forces black holes into the domain of thermodynamics. They have temperature, they emit energy, they obey the second law, and, therefore, they must participate in the great statistical ballet that rules everything from steam engines to entropy in your brain. Here's a fun fringe idea that emerged from this line of thinking, the Page curve. Named after physicist Don Page, it describes how the entropy of a black hole changes over time if information is not lost. According to the Page curve, entropy rises during the early stages of evaporation, because information is still trapped inside. But eventually it peaks, and as the black hole radiates more, the radiation starts to carry out the information. Entropy falls. The total system remains pure as quantum mechanics demands. In 2019 and 2020, new work using tools from quantum gravity, like holography and entanglement entropy, suggested the Page curve might actually be correct. This was huge. A rare moment when theoretical physics managed to claw a few answers from the black pit of confusion. You float in silence, digesting all of this. That gentle, featureless void you've been circling for hours. It's not a mute monster. It's an extremely complicated thermodynamic system. A statistical soup of microstates we don't yet understand, leaking heat and maybe even data into the universe around it. And Hawking radiation is the signal, the only clue. The last communication a black hole has with the cosmos before it slips beneath the Planck-scale veil and vanishes or explodes or becomes a grain of pure entropy somewhere beyond understanding. One final whisper, drifting outward at the speed of light. You watch the simulated particles on your display ghosting away from the event horizon, carrying heat, energy, and maybe, just maybe, a fraction of a memory. You float back just far enough to see the whole horizon again, not just as a deadly boundary or a source of heat, but as something more. Symbolic. A screen. A shell. A boundary between known and unknown. You tilt your head slightly and ask the question that thousands of physicists have whispered, groaned, or scribbled into the margins of their notebooks over the last few decades. What if everything we see inside the universe is really just projected from a surface? That, dear traveller, is the slippery slope that leads you straight to one of the most beautiful and reality-bending ideas in modern theoretical physics, the holographic principle. Take a deep breath, because this one folds space, time, and common sense into a pretzel. The idea was born from the strange behaviour of black holes. You've already learned that black hole entropy scales with area, not volume. That is, how much disorder or hidden information a black hole holds is tied to the surface of its event horizon. That's weird. It's like discovering that the amount of data in your computer doesn't depend on how many files are inside, but on how shiny the outside of the case is. And then came a bold leap, proposed by physicists like Gerard T. Hooft and Leonard Susskind. What if this is true for the entire universe? What if all the information that makes up you, your atoms, your memories, your late-night snack cravings, doesn't live inside 3D space the way you think it does? What if it's all encoded on a 2D surface, and everything you experience is just a kind of projection? Not metaphorically, literally. This is the holographic universe. And it's not just philosophical rambling, it's a direct result of trying to take black hole thermodynamics seriously. You look at the black hole now, its dark surface undisturbed, and you begin to see it not just as a hole in space, but as a kind of storage device, a screen, like a galactic DVD encoding everything that's ever fallen in, not in the depths, but on the edges. From this idea, something extraordinary emerged, the ADS/CFT correspondence. Yes, it's a mouthful. Think of it as physics' attempt to make sense of the holographic whisper. Proposed by Juan Maldacena in 1997, this duality connects two very different theories. 1. A DS, anti-de Sitter space, a type of curved space-time with a boundary, like a bowl-shaped universe where gravity dominates. CFT, conformal field theory, a type of quantum theory that lives on the boundary of that bowl. No gravity, just particles and interactions. What Maldacena showed is that these two are mathematically equivalent. Everything that happens in the bulk, the 3D gravitational world, can be described by a theory with no gravity at all, living on the 2D surface. It's like discovering that your 3D hologram of a space battle is completely described by patterns of light on a 2D film. No depth, just encoded information playing out on the edge. And black holes? They're the heart of this story. In the ADS/CFT framework, a black hole in the 3D ADS space is equivalent to a thermal system, a soup of particles, on the 2D boundary. The black hole's entropy, temperature, even its radiation, all map directly onto thermodynamic properties in this lower dimensional theory. This isn't just a metaphor anymore, it's a working mathematical correspondence. Physicists use it to calculate real things about black holes, like entropy curves and entanglement, using a much simpler shadow universe living on the surface. Historians still argue whether ADS/CFT applies to our universe. We don't live in anti-de Sitter space after all. But the holographic principle's grip is tight. It's become the guiding star for many attempts at quantum gravity, string theory, and even condensed matter physics. Now for your fringe fact of the night. Some speculative cosmologists think that even our cosmic horizon, the boundary beyond which we can't observe, might behave like a holographic screen, that the visible universe is just a 3D shadow of quantum information smeared across the edge of existence. And while this idea remains unproven, it carries a deep, oddly poetic consequence. You may be a projection, a flickering hologram, a bundle of encoded bits scrawled on a surface somewhere beyond reach, replaying a 3D drama written in 2D ink. You squint at the event horizon. Suddenly it feels less like a wall and more like a display. What you once thought of as emptiness now looks suspiciously like an interface. It changes how you think of thermodynamics too. Temperature, energy, entropy. Maybe they're not just properties of things inside the universe, but also of the boundaries themselves. Maybe space and time emerge from the laws of thermodynamics running on those boundaries. It's unsettling and thrilling, and just sleepily abstract enough to let your brain bounce between physics and dreams like a well-aimed photon. You adjust your ship's display. The simulation now shows the event horizon as a pixelated grid, each square representing one Planck area, a unit so small that even the most obsessive Lego master couldn't replicate it. Every Planck square holds one bit of information, one microstate, one tiny piece of the black hole's memory, and when matter falls in, It's stored there. The volume doesn't change, the surface does. The surface is where the action is. It always was. A black hole isn't a volume, it's a boundary with consequences. And the universe? It might be exactly the same. Now, as you float beside this holographic furnace, you realize the implications are too big to fit in your brain all at once. So you let them blur together into a single quiet impression. When you look into a black hole, it might be looking back. Not through the singularity, but through the screen, where all of space, all of heat, all of time and entropy are written in a language we've only just begun to translate. You're still floating near the event horizon, the great cosmic screen that may or may not be projecting your entire reality. But tonight we're going to mess with your confidence a bit more. Because if there's one thing physicists still haven't agreed on, it's this. Do black holes actually destroy information, or just style it beyond recognition? Welcome to the hair salon of physics, where the subject is black hole haircuts and lost information. It all starts with the infamous no-hair theorem, a charming bit of theoretical sass that states black holes have no hair. Now, in physics, hair doesn't mean literal follicles, tragically, but refers to distinguishable features, specifically any kind of identifiable structure or information beyond the basics. According to this theorem, black holes are completely defined by just three parameters: mass, electric charge, angular momentum. That's it. That's all you get. Doesn't matter if you tossed in a piano, a planet, or your entire browser history. Once it crosses the event horizon, all that detail is obliterated. What's left? Just a smooth, boring black hole with the same three tags. Or so we thought. Because here's the problem. Quantum mechanics does not allow information to be lost. It's not just a preference. It's a foundational principle. The evolution of a quantum system is unitary, meaning you can run it forwards and backwards without ever losing any of the data about how it started. So when you toss a cat into a black hole, physics demands that somewhere, in some form, that cat's quantum state still exists. But from the outside, all you get is a slightly bigger black hole. No meows, no cat-shaped wiggle on the horizon, just mass, charge, and spin. This is the infamous black hole information paradox, a conceptual tug-of-war between general relativity and quantum theory. One says the whole eats the cat and forgets it. The other says nothing can ever truly be forgotten. You squint at the black hole now. It looks unchanged, smooth as ever, but your instruments are set to paranoid, because this paradox has forced physicists to imagine that maybe, just maybe, black holes do have hair. Not shampoo commercial hair, not even well-groomed hair, but soft hair. Tiny, almost imperceptible structures on the event horizon that encode subtle differences based on what fell in. That's right, your cat might still be out there, just very flat and very encoded. In 2016, Stephen Hawking, Malcolm Perry and Andrew Strominger proposed something new: soft hair. These are subtle quantum degrees of freedom living on the black hole's surface, leftovers from the gravitational field of whatever fell in. In other words, the black hole remembers, just not in a way that's obvious. It's like a party guest who doesn't talk much but secretly logs everything into a little black notebook. These soft hair modes could, in theory, store information about the quantum states of infalling matter. Not enough to fully decode your cat, perhaps, but enough to satisfy the basic requirements of quantum bookkeeping. Historians still argue whether soft hair solves the information paradox entirely, or just styles over the cracks. Some say it's a step forward, others think it's hairspray on a blackboard. Let's step back. Remember Hawking radiation? It's thermal, featureless. That's the root of the problem. If black holes only emit random, meaningless radiation, then the information is gone forever. Burned, ashes without a record. But if the radiation is not purely thermal, if it's subtly encoded, then maybe over billions of years the information is slowly radiated back out. This would require a level of quantum entanglement that boggles the mind. It would mean that every escaping Hawking particle is entangled with everything that ever fell in, a kind of quantum whisper stretched across space and time. Some physicists even imagine the event horizon as a kind of quantum scrambler, a device that mixes information so thoroughly that the original structure is hidden, but not destroyed. It's there, just hopelessly entangled and spread across the radiation. Here's a fringe nugget for your mental snack drawer. The Hayden Preskill protocol suggests that black holes might behave like fast information scramblers. After the black hole reaches a certain point in its evaporation, what we call the page time, any new information that falls in can be rapidly encoded into the outgoing radiation. In simpler terms, once the black hole has leaked out about half of its entropy, it becomes better at sending messages back out. Like it suddenly remembers how to talk. This idea even shows up in the most surprising places, like quantum computers. Researchers are using principles from black hole dynamics to design better information scrambling systems. Turns out, the abyss is great at multitasking. But back to the question that haunts you. Does the black hole delete the cat, or just restyle it into photons and probability fields? There's no final answer yet. The math gets fractal, the theories start to contradict, and your headache gains entropy. But here's where things land, for now. Black holes probably don't destroy information, and if you're wondering whether these solutions are testable in any practical sense, not yet. Maybe not ever. A real black hole is hard to interrogate. You can't just knock on its horizon and ask what it had for breakfast. But theoretical work continues. New tools from quantum information theory, entanglement entropy, and holography are giving physicists better ways to phrase the question. Someday we might find a way to extract that soft hair data, or decode Hawking radiation like a cosmic escape room puzzle. Until then, you float in the quiet, watching the black hole spin gently, the horizon calm and unruffled. But you know better now. You know it might be storing everything. Every scream, every fall, every paradox, folded into soft ripples you can't quite see. It's not bald, it's just minimalist. You're still hovering near the horizon, the thinnest line between known physics and absolute madness. And now it's time to get your gloves dirty. Not metaphorically, we're about to sift through the rules, the laws, the unspoken, and sometimes very loudly spoken, truths that define how black holes behave thermodynamically. Because yes, black holes don't just radiate and hold entropy for the fun of it. They actually follow a set of thermodynamic laws, just like the hot cup of tea you forgot on your desk 6 hours ago. Only these laws are cosmic, and sometimes completely counterintuitive. So let's take them one by one, shall we? First, the zeroth law. Yes, physics starts counting at zero sometimes. The zeroth law of black hole thermodynamics states, the surface gravity of a stationary black hole is constant across its event horizon. In normal thermodynamics, the zeroth law says that temperature is uniform across a system in thermal equilibrium. So this is the black hole version of saying, yep, the horizon's heat is evenly spread out. But here's the kicker. Temperature here means surface gravity. That's the acceleration you'd need to hover just outside the event horizon without falling in. For a non-rotating, uncharged black hole, it's simple. But for rotating or charged black holes, it gets complex. Still, once you stabilize it, the surface gravity levels out. No hot spots, no cold patches, just one smooth, even temperature, all the way around. Nice. Predictable. Except that it's surface gravity pretending to be temperature. Already a little weird. Second, the first law. This is the heart of it all. The first law connects changes in black hole mass with changes in area, angular momentum and charge. It reads something like dm equals open parenthesis key divided by 8 pi g close parenthesis dA plus omega dj plus phi dq. Let's unpack that without making your brain fall into a singularity. dm is the change in mass, or energy. Basically it says, if you throw something into a black hole, a spinning charged something, you'll increase its mass, spin or charge, and the area of its horizon will grow in accordance. Just like how adding heat to a gas increases its energy and volume. It's a direct parallel to the first law of thermodynamics, which is all about conservation of energy. But instead of temperature and entropy, we've got surface gravity and horizon area. Because in black hole physics, area equals entropy. You lean back and admire how elegant that is. Gravity, geometry, and thermodynamics all folded into one equation. Your coffee has energy. So does a black hole. The difference is your coffee doesn't eat stars. Third, the second law. You know this one already, or at least the flavour of it. The area of a black hole's event horizon never decreases. This is Hawking's area theorem, and it's the direct black hole equivalent of the second law of thermodynamics. Entropy always increases. If you toss matter into a black hole, the event horizon expands to account for the added entropy. It doesn't shrink, it doesn't shiver, It just grows. Of course, this theorem holds only in classical physics. When you add quantum mechanics to the mix, looking at you, Hawking radiation, the area can shrink. Black holes can evaporate. But here's the fix. Even though the black hole's entropy drops, the universe's total entropy still rises. Hawking radiation is chaotic, disordered, and it carries entropy away. The second law lives on. Historians still argue whether this version of the second law is a true law or just an approximation that works until quantum gravity gets involved. But for now it holds. The void still gets messier. Fourth, the third law. Yes, we're back to actual counting now. The third law of black hole thermodynamics says it is impossible to reduce the surface gravity of a black hole to zero through any finite sequence of physical processes. Translation: you can't chill a black hole down to absolute zero in any realistic way. This makes sense thermodynamically. In ordinary physics, you can't reach absolute zero temperature with any finite number of steps. You can get close, but you'll always be radiating just a bit. The black hole version implies that extremal black holes, those that have maximal charge or spin and zero surface gravity, are theoretical ideals. You can't get there by throwing in particles or adjusting spin. They're unicorns. A fringe curiosity. Some string theory models actually love extremal black holes because they're easier to study. Their zero temperature makes the math more tractable. But in the wild, it's unlikely we'd ever see one. So that's it. 4 laws. 4 eerie parallels to normal thermodynamics, but wrapped in event horizons and surface gravity and entropy that clings to surface area like cosmic cling film. You glance again at your onboard thermodynamic display. 4 neat rows. Zeroth. Horizon's surface gravity is uniform. It's neat, beautiful even, and also vaguely terrifying. Because if these laws hold, that means black holes aren't just gravitational leftovers. They're thermodynamic objects. They participate in the same rules that govern stars, engines, chemical reactions, and you. They have temperature, they evolve, they decay, they die. And in obeying these laws, they connect 2 great realms of physics that rarely agree: general relativity and quantum mechanics. You let that thought linger. The fabric of space-time, Einstein's great masterpiece, meets the granular chaos of quantum physics in the thermodynamic behavior of a black hole. Heat and gravity, order and disorder, geometry and entropy, and you're just here to witness it, floating beside a furnace made of silence, glowing with meaning you can barely grasp. You check your sensors one last time. Nothing new, just the steady tick of Hawking radiation, the subtle shift in mass, the dance of entropy on an invisible surface. Everything's obeying the rules, even the monsters. You're still adrift in the blackness, weightless, but weighted down by laws, paradoxes, and the eerie knowledge that even the emptiest thing in the universe isn't truly at rest. But now, it's time to face the real twist in the cosmic oven. Some black holes have negative heat capacity. Yes, negative. Like an emotional support thermostat from a haunted house. Here's the strange truth. The more energy you remove from certain black holes, the hotter they get. Let that sink in for a second. You might remember from, every campfire ever, that when you take energy out of something it cools down. That's how thermodynamics works for everything from boiling kettles to sweaty joggers. But for black holes, not so fast. Let's rewind to our old friend, the Schwarzschild black hole, the basic non-spinning uncharged kind. Its temperature, as Hawking showed, is inversely proportional to its mass, T proportional to 1 over m, so if the black hole loses mass through Hawking radiation, its temperature goes up, and as it gets hotter, it radiates faster, which causes it to lose mass faster, which makes it even hotter. You see where this is going. This runaway feedback loop is what gives the Schwarzschild black hole negative heat capacity, and in thermodynamics that's unsettling. It's like watching a freezer that warms up as it loses ice. It's the opposite of stable. It means black holes are thermodynamically unstable, at least when they're radiating into empty space. There's no equilibrium point, no cozy temperature where everything just balances out. You hover in your simulation, watching the black hole shrink slightly as it emits another whisper of Hawking radiation. Its surface gravity rises, its temperature spikes, the glow grows stronger, the numbers spiral up, and in your head, a bell rings. Because this behavior isn't unique to black holes, it's actually shared by other gravitational systems, like star clusters and galaxies. When stars in a dense cluster lose energy, say by radiating light, the core of the cluster heats up. It collapses in on itself. That's gravity being greedy. Gravitational systems want to concentrate energy as they lose it. They defy the usual thermodynamic rulebook. Black holes are just the most extreme example. Historians still argue whether this negative heat capacity makes black holes break thermodynamics, or just stretch it into a shape that only gravity understands. Some researchers suggest we may need a new version of thermodynamics, a gravitational thermodynamics, to fully explain this behaviour. But it doesn't end there. Now imagine this. Instead of placing your black hole in empty space, you surround it with a warm bath, a radiation field, an atmosphere. Suddenly things get interesting. Depending on the conditions, your black hole might absorb more energy than it emits. In that case, it gains mass. And as it gains mass, its temperature drops. Yes, add heat and it cools down. It's the cosmic equivalent of eating pizza and getting thinner. Deeply suspicious, but mathematically legit. There's a particular solution to Einstein's equations that helps us make sense of this. Enter the ADS black hole. That's a black hole in anti-de Sitter space, where spacetime is curved in a very particular, negatively curved way. In this setup, something magical happens. You can have thermal equilibrium. Thanks to the geometry of ADS space, radiation doesn't drift off into the infinite void. It reflects. It bounces back. The black hole can exchange energy with the surrounding radiation and reach a stable temperature. And in this setting, something called the Hawking page phase transition occurs. This is a real, honest-to-goodness phase change, like water turning into steam, but for black holes. At low temperatures, the dominant state is just hot ADS space, but at higher temperatures it's better, thermodynamically speaking, for a black hole to exist. It's a thermal preference. The cosmos, given the choice, picks the black hole. This transition, discovered in the 1980s, was already fascinating, but it gained a second life in string theory and holography. Because under ADS/CFT duality, the Hawking page transition corresponds to a confinement-deconfinement transition in quantum field theory. Translation: the black hole's behaviour mimics that of quarks binding and unbinding inside a proton. That's right. Black hole thermodynamics might have something to say about the strong nuclear force. So now we have black holes behaving like quantum systems, undergoing phase transitions, and showing temperature behaviour that would make your high school physics teacher hurl their chalkboard eraser. Oh, and did we mention the thermodynamic volume? Yeah. Some black holes actually have something like pressure and volume too. The field is called black hole chemistry, and it treats the cosmological constant, lambda, as a kind of pressure. This lets you write black hole thermodynamics with terms like dm equals TdS plus VdP plus. Wait, what? Volume? In a black hole? Sort of. It's not a literal what's inside the whole volume. It's a thermodynamic quantity that behaves like volume in the equations. You can define things like compressibility and even do PV diagrams. Suddenly black holes are steam engines again. Quirky fact. Some black hole systems even show van der Waals behaviour. That's the same equation of state used to describe real gases. So in a very real way, your average black hole has more in common with your stovetop pressure cooker than it wants to admit. You glance back at the event horizon on your display. Just a ring of silence. But beneath it, negative heat capacity, pressure, volume, entropic fingerprints, phase transitions. The hole isn't just radiating, it's doing thermodynamics, badly, weirdly, backwards, and yet consistently. And here's the whisper you've been waiting for. Maybe these strange thermal properties aren't bugs. Maybe they're clues. Clues that gravity, at its core, is just a macroscopic illusion. That space-time is emergent. That thermodynamics came first and geometry followed. You sit with that one for a moment, let it steep. Because when your furnace gets hotter as it loses fuel, something deeper is going on. You're adrift now in a fog of equations and entropy. Your engine's idling quietly while the black hole ahead hums with thermal tension. You've seen it radiate. You've watched it heat up as it shrinks. You've even flirted with the idea that it's projecting your reality from its surface like a cosmic film projector. But now it's time to ask the question no one really wants to answer. What are the microscopic building blocks of a black hole's entropy? Because if entropy is a measure of microstates, tiny distinct ways that a system's insides can be arranged, then what exactly is going on inside a black hole? This question has haunted physicists since the Bekenstein-Hawking formula first slapped area and entropy together and called it a law. If you assign entropy to a black hole, you must assume it has internal degrees of freedom, countable ones, specific quantum states. But general relativity tells you that the interior of a black hole is a singularity, a place where space and time fall apart, where your calculator screams and your equations spill coffee on themselves. So what are these so-called microstates? And more importantly, where are they? Enter string theory. Enter the most ambitious guessing game in physics. In the mid-1990s, a string theorist named Andrew Strominger and his collaborator Qumran Vafa made a bold move. Using the tools of string theory, they constructed a model of a specific kind of black hole, a supersymmetric extremal one, i.e., zero temperature, highly charged, not your everyday neighborhood variety. It was built out of D-branes, which are multidimensional objects in string theory that can hold open strings, like tent pegs for reality. And here's the kicker. They actually counted the number of microstates. Yes, literally counted them. Not estimated, not theorized. Counted. And guess what? Their result matched the Bekenstein-Hawking entropy exactly. Boom, mic drop. Or, more accurately, chalk drop. This was huge. It was the first time anyone had managed to derive the entropy of a black hole from a statistical microscopic theory. It was like discovering the atomic structure of steam, except instead of water molecules, you had vibrating strings and membranes doing cosmic gymnastics. String theory had thrown its hat into the ring, and for once, it landed on target. But there were caveats. Big ones. This model only worked for very specific black holes, extremal ones, highly supersymmetric ones, in spaces with more than 4 dimensions. Basically, black holes that would never survive in the gritty, chaotic mess of our actual universe. Still, the success was undeniable. It suggested that black hole entropy really does come from hidden microstates, and that a fundamental theory of quantum gravity could, in principle, count them. This line of work continues today. Physicists hunt for new microstate constructions, try to map them to black hole geometries, and hope to extend these models to non-extremal, non-supersymmetric, real-world black holes. Now, let's talk about a bizarre twist in this tale, the fuzzball proposal. You float closer to your simulated black hole, but now instead of a smooth, clean event horizon, imagine something else. A tangled, knotted, stringy mess. A beach ball made of vibrating loops and membranes, all fuzzed out in space-time. That's the fuzzball. Proposed by physicists Samir Mathur and others, the fuzzball concept says this. Maybe the reason you can't define what's inside a black hole is because there's nothing inside. No singularity, no empty volume, just an enormous collection of microstates piled on top of one another, extending all the way to what you thought was the event horizon. In this view, the traditional black hole is an illusion, an emergent statistical effect. The interior is replaced by a fuzz of microstates, each representing a different way the black hole could be composed. No two are exactly alike, and crucially, there's no information loss. When something falls in, it becomes part of the fuzz, which leads to the next bizarre implication. Fuzzballs radiate information. They don't just emit thermal noise, they emit encoded Hawking radiation. Every photon carries a tiny signature of the fuzzball's specific state. Is it proven? Not yet. Is it testable? Also number. Is it wildly speculative? Absolutely. But is it solving problems the classic model can't touch? You bet. Historians still argue whether fuzzballs are elegant solutions or just desperate measures, but the debate is healthy, and the search for microstates continues. If black holes are the densest hard drives in the universe, physicists are trying to find their file systems. Let's go fringe for a moment. There are ideas floating around that black hole microstates could be topological in nature, based not on position and momentum, but on the knottedness of space-time itself. Imagine a black hole as a tangle of multidimensional spaghetti, with each twist storing information. These topological features might be immune to decay and radiation, preserving data even as the black hole evaporates. Some researchers go further and claim that microstates might not exist inside the black hole at all, but on its surface, encoded in holographic patterns, tangled fields, or quantum entanglement structures we haven't fully mapped yet. And that brings us to one of the most influential metaphors in all of this. A black hole is a thermodynamic ensemble of possible microstate geometries. In other words, what you perceive as a smooth black hole is actually an average, a blurred image composed of countless microstate geometries, all coexisting in the quantum foam. You're not looking at one object, you're looking at the statistical impression of many. And that ties back to what entropy really is, a measure of how many ways the system could be arranged deep down behind the curtain. You stare at your own reflection in the viewport for a moment and wonder, how many microstates are you made of? And how many ways could the universe write your atoms, your thoughts, your dreams, across the pixels of space-time? Because if a black hole has microstates, maybe everything does. You hover in stillness now, the black hole spinning quietly below like a clock with no hands. No ticking, no gears, just a faint ripple of entropy, a leak of energy, and the strange suspicion that heat and gravity are more alike than anyone ever expected. So tonight, you're not just orbiting a black hole, you're circling a realization, one that physicists have been edging toward for decades. What if gravity itself is thermodynamic, not just related to thermodynamics, but emergent from it? Like temperature rising out of molecular motion, maybe gravity isn't fundamental at all. Maybe it's the cosmic version of steam. Let's take a slow step into the deep end. In classical physics, gravity is a force. In Einstein's general relativity, it's the curvature of space-time. Mass tells space how to bend. Space tells matter how to move. It's all very elegant. But if black holes have entropy, if they radiate heat, if they follow thermodynamic laws, then there's a chance, just a whisper, that gravity isn't telling the full story. In the 1990s, physicist Ted Jacobson proposed something radical. He flipped the script and asked, what if the Einstein field equations, those sacred, beautiful tensors, are actually the thermodynamic equations of state for spacetime? In his paper, Jacobson showed that if you assume 1, the entropy of a region is proportional to the area of its boundary, then you can actually derive Einstein's equations from these assumptions. Let that sink in. He didn't start with geometry and then find thermodynamics. He started with thermodynamics and derived gravity. It's like waking up one day and realizing that the reason your coffee cup falls to the floor isn't because of some deep geometric truth, but because the entropy gradient told it to. You feel a chill, not from fear, but from awe. If Jacobson is right, then space-time curvature isn't the root of reality. It's just the low-energy expression of deeper thermodynamic principles. Gravity is emergent, like temperature in a gas, like pressure in a balloon, like every macroscopic thing that arises from a microscopic sea of chaos. This idea led to a broader wave of research into what's now called emergent gravity, and the examples kept stacking up. Let's talk about entropic gravity, proposed by physicist Eric Verlinde. Verlinde suggested that gravity might arise as an entropic force, a force that emerges from the statistical tendency of systems to move toward more probable configurations. In this view, the force of gravity is just the result of information being rearranged in the presence of mass. It's not a fundamental interaction, it's a shadow of entropy doing its thing. This model reproduces Newton's law of gravitation in the right limits, and even suggests tweaks at galactic scales, possibly explaining dark matter without needing to invent dark matter. Fringe? Definitely. But serious physicists are listening, because if gravity is thermodynamic at its core, it might explain more than we ever imagined. Now here's a quieter, weirder twist, the Unruh effect. When you accelerate through a vacuum, say, in a spaceship or a thought experiment, you don't see emptiness, you see heat, a thermal bath of particles just sitting there. The faster you accelerate, the hotter it gets. This effect, predicted by William Unruh in the 1970s, connects acceleration, temperature, and horizons. And black holes? They're just extreme versions of this. Their horizons are the ultimate acceleration boundaries. Their temperatures are Unruh heat cranked up by mass. So again, heat and gravity, bound together, unbreakable. And this isn't just a poetic link, there's math behind it. The connection between black hole temperature, surface gravity, and Unruh radiation draws a continuous line from thermodynamics to the deepest fabric of spacetime. You float now in a zone of paradox. Gravity, the oldest force, the one Newton found under a tree, might not be a force at all. It might be an illusion born from entropy, But that illusion is powerful. It holds galaxies together. It bends time. It creates black holes. It runs the universe. You check your display. The temperature near the event horizon is still climbing, slowly but surely. Every burst of Hawking radiation is the result of quantum fluctuations on the boundary of space-time. Every lost particle is tied to the curvature of the horizon, and all of it follows rules that look suspiciously like the rules of heat. Here's a historical nudge. Before Jacobson, before Verlinde, before holography was mainstream, there were hints of this. In the 1970s, physicist Jacob Bekenstein said that information is physical, that entropy isn't just disorder, it's a measure of what we don't know about, the internal configuration of something. And black holes? They're the universe's most efficient information scramblers. If that doesn't scream statistical mechanics, nothing does. Let's toss in a quirky tidbit. Some researchers are exploring the idea that quantum entanglement is what builds space-time, that the geometry of the universe is made of entangled information, that if you break the entanglement between regions, space itself falls apart. This leads to the phrase you'll hear in the back corners of seminars, geometry from entanglement, a whisper, a hint, a roadmap, and in the middle of that roadmap, black hole thermodynamics. Because black holes are the places where all of this meets: heat, gravity, entropy, information, entanglement, and collapse. They're not just astronomical curiosities, they're the universe's most honest systems. No frills, no fluff, just pure physics, playing all the instruments at once. You glance back at the black hole, it doesn't do anything special, it doesn't pulse or glow, but now you see it differently. It's not just a gravitational well, it's a thermodynamic engine, a quantum information vault, a space-time whisperer, and maybe, just maybe, it's the reason you experience space at all. You feel it before you see it, a tremble in your simulated sensors, a warping of logic, a gentle nudge that says, the equations are about to get argumentative. You've drifted so deep into black hole thermodynamics that now you've reached the event horizon of sanity itself, and waiting for you here, as promised, are the rebels, the radicals, the paradoxes, the speculative jungle of competing theories that physicists still bicker over in both published journals and late-night hallway debates at conferences. Yes, friend, it's time to face the newest generation of mind melters, firewalls, fuzzballs, and other paradoxes. Let's open with the most incendiary one, the firewall paradox. Imagine you're an astronaut with questionable decision-making skills. You decide to fall into a large black hole. According to Einstein, as long as the black hole is massive enough, you wouldn't feel anything unusual crossing the event horizon. No heat, no pressure spike, not even a change in your playlist. That's the principle of equivalence in general relativity. Locally, physics feels the same whether you're floating in empty space or falling into a gravitational abyss. The event horizon isn't a wall, it's a coordinate trick, a boundary you cross like slipping into a warm bath, if warm baths were permanently one way. But now toss in quantum mechanics and things get spicy. In 2012, physicists Almheri, Marolf, Polchinski, and Sully, we'll call them AMPS because that's what theorists do, proposed something disturbing. To resolve the information paradox and preserve unitarity in quantum mechanics, they concluded that something radical had to happen at the event horizon, namely, you burn. According to AMPS, the event horizon isn't smooth. It's a wall of high-energy particles, a firewall that incinerates anything crossing it. Why? Because of a contradiction in how quantum entanglement is supposed to work near a black hole. Here's the boiled-down tension. To preserve information, the outgoing Hawking radiation must be entangled with the earlier radiation. That's how the total state stays pure, so something has to give. AMPS argued, it's the horizon, and so the firewall was born. It's a violent answer. It means general relativity fails at the horizon. It means no more peaceful plunge into the void. It means the equivalence principle, the very heart of Einstein's theory, is broken by quantum mechanics. Physicists were not amused. Stephen Hawking, for one, wasn't convinced. He suggested that maybe information never crosses the horizon in the first place. Instead, it's reflected, scrambled, and emitted back out, essentially turning the horizon into a holographic quantum mirror. No firewall required. But the debate rages on. Historians still argue whether firewalls are physical realities, mathematical misinterpretations, or just temporary scaffolding until someone comes up with a better quantum gravity theory. But one thing's clear. Something weird happens at the horizon, and we don't fully understand it. Now let's change channels. Same paradox, different costume. Enter fuzzballs. Remember these from a few sections back? They're the string theory alternative to traditional black holes. In this view, there is no smooth horizon, no interior, no singularity. Instead, each black hole is a tangled mess of stringy microstates, each one a fully formed horizonless geometry. What looks like a black hole from a distance is actually the statistical average of many such fuzzballs. And here's the kicker. Fuzzballs don't have firewalls, because they don't have traditional horizons at all. You don't cross into empty space, you crash into the fuzz. The radiation that escapes is not thermal noise, but quantum-specific, fully entangled Hawking radiation. No information is lost, no need to violate unitarity or destroy the equivalence principle. Of course, this is still highly theoretical. We've only constructed fuzzball solutions for very specific kinds of black holes, supersymmetric, stringy, higher dimensional ones. Whether fuzzballs exist for real, astrophysical black holes, unknown, probably unknowable, but compelling. And then, because physics is nothing if not aggressively thorough, there are even more radical ideas. One such idea is the ER equals EPR conjecture. Proposed by Juan Maldacena and Leonard Susskind, this hypothesis says that Einstein-Rosen bridges, also known as wormholes, and Einstein-Podolsky-Rosen entanglement might be two sides of the same coin, that entangled particles are connected by tiny, non-traversable wormholes. Yes, you heard that right. If two particles are entangled, no matter how far apart, they might be geometrically connected by a microscopic wormhole. Apply this to black holes, and it suggests that the entanglement between Hawking radiation and the black hole interior might literally be a bridge, a space-time tunnel made of quantum information. This elegant twist could help preserve unitarity while explaining how information escapes. But it also leans heavily on string theory, holography, and theoretical scaffolding we still don't have full access to. Still, it's better than fire. Let's toss in one more brainbender before we glide away. Complementarity. This idea, championed by Susskind and others, says that maybe no single observer can access both the inside and outside information of a black hole. From the outside, information is reflected, scrambled, and radiated out. From the inside, the infalling observer sees a smooth horizon and no drama. Both realities are valid, but mutually exclusive, kind of like quantum physics doing a magic trick where both truths are real, but only depending on who's watching. You can't test both perspectives simultaneously. You can't violate causality. You just have to accept that space-time is playing two games at once, and you're only invited to one. It's like a cosmic magician performing a disappearing act. The bunny is either gone, or it's behind the curtain. But if you look too closely, the whole illusion unravels. You drift back now, watching the event horizon swirl. You know more than you did. But you also know that knowledge is fragmenting here. The closer we look at the horizon, the more the answers blur. Every theory, firewalls, fuzzballs, wormholes, quantum complements, they all want to preserve the laws of physics. They just can't agree on which ones to bend. So you sit with that discomfort. It's part of the deal. Black hole thermodynamics doesn't resolve neatly. It burns neatly. It evaporates predictably. But when it comes to the nature of horizons, information, and reality itself, there are still too many endings, too many whispers in the equations, and in the background, one soft, inescapable truth. You can fall in. But understanding what happens next, that's still an open problem. You coast in silence now, with the black hole fading behind you, like a dying star in the rearview mirror. You've watched it spin, radiate, scramble, whisper, defying expectations and rewriting laws in real time. But now it's time to face the final act of this long, slow, thermodynamic death. Yes, tonight, you're sitting vigil for a black hole as it evaporates into nothing. This is the end game, the quiet apocalypse, the death by evaporation. It begins innocuously, a trickle of Hawking radiation, nothing dramatic. Just a slow, cold leak of energy that you wouldn't even notice if you weren't watching carefully for a few billion years. A stellar mass black hole takes longer to evaporate than the current age of the universe by a factor of 10 to the power of 60. That's one followed by 60 zeros. If you wanted to watch one fully vanish, you'd need a chair made of frozen time and the patience of a heat-dead god. But that slow leak never stops. Every moment another wisp of radiation escapes, another sliver of mass disappears, the black hole shrinks, its temperature climbs, and its rate of evaporation accelerates. It's a long fuse with an explosive end. You watch the numbers flicker across your display. The mass drops, the entropy falls, the horizon contracts, all smooth, all consistent. But then, something changes. As the black hole loses the last chunk of its mass, its temperature skyrockets. Hawking radiation pours out faster and hotter. What began as a gentle mist turns into a raging thermal flare. In the final moments, perhaps seconds, perhaps nanoseconds, depending on the mass, the black hole undergoes a runaway evaporation, and then it's gone. No bang, no gravitational collapse, no singularity snapping shut, just a flash, a gasp, a whisper of heat, and silence. This is the most terrifyingly quiet death in the universe, a complete vanishing act, done with all the flare of a dim bulb flickering out. But the consequences? Oh, they're anything but quiet, because now you're left with questions that burn brighter than any final radiation burst. Where did the information go? This is the core of the information paradox you've been circling all along. If the black hole is truly gone, nothing left, not even a remnant, then where is the record of what fell in? All those atoms, books, stars, socks, and quantum states, just gone. The final stage of the evaporation is where theory breaks, where physics holds its breath. Because quantum mechanics demands that the total state be pure, that information is conserved, that you can, in principle, rewind the universe and get your socks back. But if Hawking radiation is purely thermal, and the black hole truly disappears, then there's no way to recover that information. The quantum movie can't be played in reverse. That's a violation of unitarity, and the universe does not allow that. So, possibilities. Option 1, remnants. The black hole shrinks down to a Planck-sized object, infinitely dense, eternally stable, no longer radiating. It holds all the information inside like a tiny cosmic USB drive you can never read. This solves the paradox but creates others. These remnants would have to be infinitely diverse, able to store infinite information in finite space. They'd clog the universe with weird, undetectable debris. Option 2. Information escapes in the radiation. The Hawking radiation isn't perfectly thermal, it's subtly encoded, entangled, meaning that, over time, the information leaks out in the radiation itself. This would preserve unitarity, satisfy quantum mechanics, and align with the page curve we talked about earlier. Problem is, this would require some mechanism to preserve long-range entanglement across space-time. No one's quite nailed that down. Option 3, the holographic solution. Maybe the black hole was never storing information inside at all. Maybe it's always been on the surface. The radiation, then, is a slow unravelling of a 2D record, a holographic printout, burned into space-time, gradually re-emitted to the universe in quantum Morse code. Option 4, quantum gravity rewrite. Maybe we're just wrong. Maybe our tools, general relativity, quantum field theory, aren't enough. We need a full theory of quantum gravity to explain what happens in the final moments. String theory, loop quantum gravity, or something no one's dreamed up. Yet. Until then, we're guessing. Historians still argue whether Hawking radiation itself is enough to resolve the paradox. After all, we've never observed it directly. No telescope has caught a black hole sneezing out photons into the void. Everything we've discussed is theoretical, beautiful, consistent, but untested. That might change. In the far future, when the universe is much older and colder, and all the stars have gone out, the last things that shine will be evaporating black holes, slowly dying, quietly leaking, the final fireworks of a heat-dead cosmos. This era has a name, the black hole era. It stretches trillions of years into the future, after galaxies fade, after protons decay, if they do, after everything else goes still. Black holes will remain, the last storytellers, radiating into silence. Eventually even they will go, one by one, the stellar ones, the intermediate mass ones, even the supermassive beasts at galactic cores. All of them will fizzle out, and the universe? It will be dark, cold, still. The last traces of entropy drifting outward into infinite space. But maybe, just maybe, encoded in that final heat is a record of everything. Every fall, every collapse, every photon, every choice. You glance at your monitor, no more black hole, just the echo of a temperature spike, a dying warmth from a thing that should have been eternal. A star collapsed, a hole formed, entropy grew, radiation escaped, and now nothing. Or everything, just very well hidden. The black hole is gone now, but you're not leaving. Not yet. You're still adrift at the event horizon's ghost, surrounded by nothing but whispers in the equations and the afterglow of quantum radiation. What remains is not mass or matter, but a lingering question. What's inside a black hole? You've circled around this question for thousands of words, danced on the boundary but never quite gone in. You've peered at the surface, decoded the entropy, followed the heat, but inside, that's where physics breaks. So in this section, you're diving, conceptually of course, into the realm where space-time curls in on itself, where time becomes space, where known laws sputter and collapse into something entirely new. You're going to swim through quantum foam and try to glimpse what quantum gravity might say about the real interior of a black hole. Let's start with the obvious. We don't know. General relativity tells you that once past the event horizon, you're on a one-way journey to the singularity. But relativity doesn't account for quantum effects. And quantum mechanics, our most precise theory ever, doesn't know how to handle curved spacetime with infinite density. The result? A theoretical void, a space where math gives up. To bridge that void, we need quantum gravity, that elusive, long-sought theory that unifies general relativity and quantum mechanics. It's the holy grail of physics, and black holes are its most promising testing ground. Let's walk through a few of the best contenders. Loop quantum gravity, LQG loop quantum gravity, takes a different approach than string theory. It doesn't add extra dimensions or strings, it quantizes spacetime itself. In this model, space is made of tiny, discrete loops, like a woven mesh of Planck-scale threads. It's not smooth, it's granular. Zoom in far enough, and geometry becomes pixelated. In this framework, a black hole isn't an empty shell, it's a knot of quantum geometry. In 2005, researchers using LQG managed to derive black hole entropy by counting the quantum states of the horizon area. Like string theorists did with D-branes, loop theorists did with spin networks, tiny loops that intersect the horizon, each one contributing a bit of entropy. And inside, LQG suggests that the singularity doesn't exist. Instead, the collapse is halted by quantum pressure. Spacetime gets compressed, then bounces. This leads to a wild idea. Maybe black holes are connected to white holes. White holes are the time reverse of black holes, regions that only emit matter, never absorb it. In some LQG models, the singularity is replaced with a bounce that transitions the interior of a black hole into a white hole over cosmic timescales. Information wouldn't be lost, it would just come back out, much, much later. You raise an eyebrow. A black hole that explodes into a white hole after eons? It's speculative. But it's surprisingly consistent with some versions of Hawking radiation and unitarity. And it gives us a possible inside. String theory's approach. Now you drift toward the other major framework. String theory. In string theory, particles are not points, they're tiny vibrating strings. Different vibrations equals different particles. It's beautiful, it's elegant, and it requires extra dimensions, usually 10 or 11 depending on the flavour of theory. And when it comes to black holes, string theory says something wild. The interior might not even exist in the way we think. In certain solutions, string theory replaces the singularity with a dense state of strings and brains, the infamous fuzzball we've already met. In this view, the classical black hole geometry is just an average, and what actually exists is a massive collection of quantum microstates. No horizon, no singularity, just a dense, messy ball of information. From the outside, it looks like a black hole. From the inside, well, there is no inside in the classical sense. You're not entering a region of curved spacetime. You're interacting with the quantum state of 1,000-folded dimensions. It's not comfortable, but it does preserve information. And here's the twist. String theorists have shown that some fuzzball solutions are smooth and horizonless. That means they solve the information paradox without a singularity and without firewalls. But, again, these only work in special cases, supersymmetric, high-dimensional theoretical black holes. So what's in your black hole? The kind sitting in the center of a galaxy? We don't know. Not yet. Quantum foam and beyond. Now let's go even deeper. At the Planck scale, the scale where quantum gravity becomes unavoidable, space-time itself isn't smooth. It's turbulent, chaotic, a boiling mess of quantum fluctuations. This is what physicist John Wheeler called quantum foam. At this scale, black hole interiors might not be smooth funnels or even strings. They might be topological mazes, constantly fluctuating geometries, wormholes forming and vanishing, tunnels linking different regions of space-time. In this chaotic soup, time may not function the way we understand it. Cause and effect break down. Space doesn't mean distance. Particles might not have definite identities. The singularity, it might be smeared out, dissolved into a topological defect, a kind of space-time scar, not a point, but a structure. And if that's true, then entropy, what you've been obsessing over for 18 sections, might not just be about surface area. It might come from degrees of freedom buried in the topology of this foam. Other theories. Let's sprinkle in some speculative spice, shall we? Asymptotic safety, a theory that tries to make gravity well-behaved at high energies by finding a fixed point where it remains predictable. Each of these tries, in its own way, to peel back the veil and say something, anything, about what lies inside. Historians still argue whether any of these theories will win. Maybe we're just looking at the same elephant from different angles. Maybe none of these are right. Maybe we'll need a new language entirely, something beyond mathematics as we know it, to describe what happens at the Planck scale. And you? You sit quietly in the cockpit, staring into the space where the black hole used to be. There's nothing there now, but your mind fills the void with foam, loops, strings, and scars. You picture a region where geometry evaporates, where time smears, where information isn't destroyed, but isn't exactly stored either. A place where space itself is born and dies in flickering flashes, and maybe, just maybe, black holes are the price the universe pays to stitch itself together. The engines hum softly now. The horizon is gone. The simulations are silent, and all that remains is the lingering heat of questions, unanswered, half-answered, or possibly unanswerable. But before you drift off completely into cosmic dreamland, there's one more thing to consider. Why does any of this matter to you? You, floating in a chair, tucked under a blanket, watching a slowly evaporating slideshow of theoretical physics. Why should you care that the darkest things in the universe are running a hidden thermodynamic game? Why should it matter that black holes radiate, that entropy clings to their surface, that they may or may not destroy information, host firewalls, hide fuzzballs, or spawn baby universes out of quantum foam? Because what black holes reveal, quietly, insistently, is that the laws of heat, chaos, and information apply to everything. Even to nothing. Let's unpack that. When Bekenstein first proposed that black holes have entropy, he wasn't trying to revolutionize physics, he was trying to protect it. He saw a conflict between the second law of thermodynamics and black holes' appetite for swallowing anything and everything. If entropy could just disappear behind a horizon, then the universe was breaking its own rules. But by demanding that black holes follow those rules, that entropy increases even in the presence of a gravitational abyss, he opened the door to an entirely new vision of the universe, one where thermodynamics isn't just a useful tool, it's the foundation. We usually think of gravity as a geometric effect, thermodynamics as a property of large systems, quantum mechanics as something that governs the very small. But black holes pull all of these threads together into one tangled knot. You throw something into a black hole, the hole grows, its entropy rises, its surface area expands. Eventually it radiates that information back out, scrambled, encoded, sometimes whispered in particles you can't even measure. And in doing so, it reminds you of something you already know deep down, that information matters, that nothing is ever truly lost. That entropy is not the enemy of the order, but the record of change. That memory is written into the universe, whether in photons or Planck surfaces. Even more than that, black holes teach you that boundaries matter. The event horizon, the edge beyond which light can't escape, isn't just a danger zone. It's a place where physics reorganizes itself, where thermodynamics steps up and says, "I've got this." Where entropy, energy, time and space all meet in one concise burning equation. It's the universe drawing a line and saying, this is where things change. And if the rules of black hole thermodynamics apply at the horizon, where else do they apply? The holographic principle whispers, everywhere. It hints that you too may be a boundary, that your body, your memories, your thoughts are surface phenomena, manifestations of deeper processes, that your experience of reality is the projection of some deeper code written on the edges of something even stranger. And maybe that's what gravity is, a heat map, a story told by entropy as it rearranges the universe from the inside out. You stare into the darkness ahead. There's no black hole in sight now, no jets, no accretion disks, just the quiet hum of the ship and your own breath echoing inside your helmet. But you can feel it still. Not the pull of gravity, but the pull of understanding. The way black holes tug on ideas, on structure, on certainty. They unravel equations, stretch time, and reduce entire galaxies into puzzles of entropy and temperature. And yet, through it all, they obey the same laws as your cup of tea. Heat, change, decay, information. Maybe that's the point. That black holes, these colossal engines of destruction, don't break physics. They confirm it. They stretch it, twist it, question it, yes. But in the end, they fall in line. They radiate. They vanish. And they leave behind only entropy, memory, and a silent mark on space-time, just like everything else. So why should this matter to you? Because in a universe governed by entropy, you are a black hole, in miniature. You absorb light, you store information, you change, you age, you radiate your energy into the world as heat, as thoughts, as love, as entropy. And eventually you vanish. But not without leaving something behind. Not without raising the temperature of the universe, however slightly. Not without increasing the disorder just enough to write your own name into the cosmic ledger. And if black holes can do that with such terrifying silence, imagine what you can do with your voice. You let your eyes close now, mind buzzing softly. No event horizon, no radiation, just warmth, curiosity, and the faint hope that somewhere, out there, the laws still hold. That heat still means something. That change is still allowed. That nothing, even a black hole, gets to opt out of the story.